Welcome everybody. Welcome to our monthly meeting this week. This week I'd like to welcome Professor Brian Boyle to do the talk. Brian has had a very full career in astrophysics, and he's going to talk through some of that. Some of the highlights, I guess, he's a former director of the SKA, and he was a project director for the Australian-New Zealand SKA bid. He has been part of Nobel Prize winning teams doing really incredible physics that he's going to talk about tonight. But enough about that. One thing I do need to mention is Brian is down in Queenstown where they're having quite a bit of weather at the minute. So his internet connection was a little bit choppy earlier on, but it looks like it's settled down now. So if we do lose his video, apologies for that in advance. But for now, I'd like to hand over to Brian. Welcome, Brian.
Thank you, Steve. Well, first, I'd like to acknowledge the Ngāi people, who are the traditional custodians of this amazingly beautiful land, which I count myself very privileged now to be a resident. As Steve said, I'm kind of pretty much former everything, and I've chosen this wonderful part of this world and this equally wonderful country to start the next step of my big adventure. So thank you all for listening in tonight. This is the first time I've done a public lecture remotely, so apologies if I sound a little bit stilted or I get a little bit boring, because I'm lacking the general feedback that I normally get from audiences. You know, when I can go into an audience and crowd surf the audience, I know they're enjoying it. So this is a bit more action at a distance, so hopefully it's okay for everybody. So welcome to Astronomy Ancient History 101. When I first spoke to Bill and asked him about what he'd like me to talk about, he picked something that was done about 30 years ago. Now, it's interesting to note that even though it's 30 years old, there are echoes of what we were doing 30 years ago in contemporary astronomy. And I'll go into that in a little bit more detail. But this is really the story of my personal journey in working with the Supernova Cosmology Project team 30 years ago, where we discovered that the universe was accelerating, hence the title of my talk. Now, it was a fascinating journey, and I should say at the outset that I only played very much a homeopathic role in this large collaboration. And by that, I mean, you know, where my contribution was effectively diluted to zero. There were far many more people in that collaboration that did wonderful things. I played a small, almost insignificant role. But nevertheless, I thought it might be interesting for people tonight just to hear about the journey that the team made to get to what eventually, of course, was rightfully awarded the Nobel Prize to the team leader. So let's start back in the 1980s. Cosmology in the 1980s, one could say, was a search for two numbers. One number being the expansion of the universe, as represented by the Hubble constant. And in the end of the 1980s, the Hubble constant, depending which camp you were in, was either 50 kilometers per second per megaparsec or 100 kilometers per second per megaparsec. That is, for every megaparsec, or 3.6 million light years from Earth you went, the universe was receding a little at 50 kilometers per second more than before, or 100 kilometers per second. And the interesting thing was that these two camps couldn't reconcile because the errors on both those numbers were about 10% of the difference between the numbers. So essentially, you paid your money and you took your choice. Similarly, the deceleration parameter of the universe, that is by how much the expansion of the universe was slowing down, was similarly unknown, or at least had a huge error bar. All the way, now we modeled this as something called Q naught. Q naught ranged from almost zero, that is, the universe was almost empty, and the material in the universe wasn't slowing it down at all due to gravity, or to a rather large number of 1.6. Q naught essentially was measuring the mean mass density, which we called omega. It was half of omega. So that if omega of the universe was 1, the mean mass density was a critical, that meant the universe would expand forever, but slow down such that the universe expansion would essentially stop, but at time of infinity. Whereas if the amount of material in the universe was less than the critical density, or omega matter was less than 1, the universe would expand forever. The acceleration, although it was slowing down, it would never stop, and we would keep on going. If the mean mass density of the universe was bigger than 1, essentially there was enough material in the universe due to gravitational forces to bring it all back together again and end up in a big crunch, the opposite of the Big Bang. And in the 1980s, we had no idea. The value of Q naught that we measured, which essentially was a direct measure of the mean mass density of the universe, could mean either that omega matter was 1 or less than 1 or more than 1. So we didn't really know what the fate of the universe was. Now, lurking in the background, although nobody really believed it, was something called the cosmological constant, or lambda, the Greek symbol lambda, which I've shoved up in the top corner here. In 1982, when I was an undergraduate, I was told by one of the famous cosmologists who taught me cosmology that lambda was an evil concept, and that although formally you had to be taught it, it didn't exist and I should ignore it. So that's what most people did. And in fact, the universe, as far as they were concerned, contained matter, so that you could describe it, everything as, the mean mass density of the universe, plus, of course, energy from light. That's where we were. That Einstein had only introduced in order to make the universe not expand, because when he did his general relativity, the universe wasn't observed to be expanded, and then later retracted it. His greatest mistake, of course, was due to the fact that the universe had been then subsequently shown to be expanding by Hubble. So that's where we were. Steve, how am I doing for quality? I just got a bad network on my message there.
Yeah, you had a little bit of an interruption there, but we're still good. I might interrupt you and tell you to turn your video off if it does get worse, but we're all good at the minute.
Yeah, unfortunately, I can't say to the audience, do you want my video off? Because I'd get a resounding chorus of, yes, turn it off.
Well, nobody's mentioned it in the comments yet.
Okay. There we go. So, where am I? Yes. So, so we began. So how do you actually go about finding out these numbers? So the expansion. So what you have to do, of course, is measure distant objects, galaxies, and you have to measure how fast they are moving away from you. Now, that's actually relatively simple to do. You disperse the light of a different galaxy to get a spectrum, like you see here. And the faster the galaxy is moving away from you, the more the characteristic fingerprint of the galaxy, its signature, the more of its colors are shifted towards the red, the famous red shift. So that's very simple. You can measure the direct velocity of recession quite simply. If you have a big enough telescope and you're able to disperse the light of these very faint galaxies. So once you have the velocity, all you need to do is to measure the distance to these objects, so that you can then work out by how much that velocity is changing as you go further and further away. And that's the problem. Measuring distances in the universe is quite difficult. It's not as if you can put down a ruler and measure all the way to the distant object. So we have to use an inferred distance. And that inferred distance is by using an object that we know has a fixed brightness or a fixed size as a function of distance from us. So when we measure how bright it is or how large it is, we can infer how far it is away by extrapolating back to the known fixed brightness of similar objects near to us. And this is called the standard candle or the standard ruler approach. Now, the challenge is, of course, that as one is looking further out, one's looking further back in time, and so you're actually seeing the universe evolve. So you have to find something that intrinsically doesn't change with cosmic time. Things can get brighter or dimmer, or they can get bigger or smaller with time. It's actually really difficult to find something whose physical properties remain fixed in time. And at the end of the 1980s, probably the best standard candle being proposed was a supernova, a stellar explosion. In this case, a supernova which was fueled by a white dwarf exploding in a binary star system, what we then called a supernova type 1a. In this scenario, you have a binary system, you have a white dwarf star, essentially a star at the end of its life, in orbit around another star, actually, and material, because the two are gravitationally interacting, is coming off the other star and funneling onto the white dwarf. Now, physics tells us that white dwarfs can have a maximum size of 1.4 times the mass of the sun. And when the material from the other star dumps onto the white dwarf and exceeds 1.4 solar masses, then the white dwarf star explodes in a huge explosion fueled by the nuclear energy of transforming the mass that's fallen onto it into energy. And because this happens at a precise mass for the white dwarf, that brightness is precise as well. So we know that the white dwarf explosion, or the supernova type 1a explosion, is constant throughout cosmic time. And indeed, that's actually borne out by observations. In this graph here, you can see a light curve in terms of its brightness of a type 1a supernova as a function of the time of its explosion. Its peak brightness occurs when the star explodes on day 0 and then tails off gradually. But this diagram, with all the different colors on it, shows many, many observations of supernovae type 1a. And it is remarkable. These are all different distances, different types of objects. And it's remarkable that they all have the same peak brightness, about 5 billion times that of the sun. So here we have a supernova 1a. We know its peak brightness, billion times the mass of the sun, and we can measure the redshifts of these objects. So we can actually start looking at how these objects, not only do we have their measure of their recession speed, but we've also got an indirect measure of their distance from us. And so with this, of course, armed with these two things, we can go ahead and try to measure how the universe is expanding and how that expansion itself is decelerating. There's one problem with that. These supernovae type 1a are pretty rare. There's less than 1 per century per large galaxy. So it's like kissing frogs. You've got to kiss a lot of galaxies before you find your supernovae type 1a. And so typically, you would have to observe 100,000 galaxies in a typical observing session in order to find even just one supernova type 1a. And there's the challenge. But it's a challenge that you can rise to. And here is a little montage of the type of experimental approach that our team was involved in. You take lots and lots of large-scale pictures of the sky, typically 50 or 100 during an observing session, and you go through in painstaking detail every single little smudge on that image. Each of those smudges is a distant galaxy. You then take the same image of the sky 3 weeks later, and you look for differences, for supernovae that have actually exploded during those difference between the first time you took the photo or the image and the second time. And this one shows you a supernova discovered in 1998 in a very, very faint galaxy. And you can see in this diagram just how challenging the observations is. It's a faint smudge going off to the bottom of one galaxy. And when you difference one from the other, you can see this faint blip. The Hubble Space Telescope image, because the main image is actually from the Cerro Tololo Observatory ground-based. So you can actually see the faint smudge in the Hubble Space Telescope. So you might say, well, Brian, you've shown me that there's a bright blob there. You haven't shown me it's a supernova. And that's a really good point, because you really got to follow these things up by, of course, dispersing the light, measuring the spectrum of these things, not only to confirm, of course, it's a supernova, but to work out its recession velocity. And of course, this is what you do. Once you've got the images, you then go to a large telescope, you disperse the light energy, you make a spectrum, you look at its intensity, and you can see the characteristic fingerprint of a supernovae type 1a, a white dwarf explosion. And in this diagram, you can see this intensity map against wavelength, and these big dips are actually caused by silicon and iron in the spectrum of the object, which is the outer layers of the star being blown off in the explosion. But of course, you'll notice the dates here. 1998 for the image detection. It's a different supernova that was followed up. I'm showing here just as an example in 1994. I'm kind of getting my head of myself, because the story really started in 1998 with this terrific team of people. And a little bit about astronomical sociology now. So I really need to give credit to a few people in this image as being the real instigators behind this. First of all is the person who's third from the left, is Carl Pennypacker, who hailed from Lawrence Berkeley Laboratory. And Carl really began this project off. He'd read a paper written by the person standing on his right, Warwick Couch, about discovering a distant supernova, a supernova at a redshift of 0.3, or about 40% back towards the beginning of the universe. Now, Warwick, a New Zealander, was working at the Anglo-Australian Observatory at the time. And Carl Pennypacker had designed a system that would give the Anglo-Australian Telescope a very, very wide field of view, the sort of wide field of view that you need in order to image lots and lots of galaxies, to kiss lots and lots of galaxies before you find your prince supernova. And he'd phoned up Warwick, having read the paper about Warwick discovering a high redshift supernova with a Danish group, and said, Warwick, you're working at this telescope. I've got a device that can give your telescope a very wide field of view. How about us working together and building something for your telescope? Warwick said, absolutely, yes. And Carl and his team came down with Heidi Marvin, now Heidi Newberg, and Shane Burns, and most importantly, Saul Perlmutter, who was Carl's postdoc working back at LBL. I had the great fortune at that point to also be working at the Anglo-Australian Observatory as a young postdoc. And Warwick very kindly invited me into the team, not because I was particularly interested in supernovae, but I was interested in doing large-scale structure of the universe. And I thought, and Warwick thought as well, that I could actually use the data gathered not to find supernovae, but to look for things like quasars that I was more interested in at the time, and to do other large-scale statistical projects. So we began the project using a new system, the Anglo-Australian Telescope. It was a system that gave the Anglo-Australian Telescope a focal ratio of f1, believe it or not. We were working with the latest generation of Charles Couple devices, a 1 megapixel camera, and giving us a field of view of the telescope of 1/4 of a degree square. And this was almost unheard of in those days, to have such a large field of view on such a large telescope. So we could image lots of galaxies very faintly and do the work of discovering our standard candle. Unfortunately, 1988 and 1989 were two of the wettest years on record in New South Wales. And our strategy of observing on one night and then observing on another night 3 weeks later was largely put paid to by the fact the weather did not cooperate. Another problem, when you think about it, is something that we probably should have, well, certainly should have thought about beforehand, is that with 1 arcsecond pixels on the camera, the galaxies that you're looking at are only about 2 arcseconds. So trying to find the faint blip on the side of the galaxy becomes a very, very difficult exercise. Now, we managed to find a few. And of course, as I said, you've got to then follow it up doing spectroscopy on another telescope. And what we did was we sent out candidate supernovae and this was kind of internet. This was while the internet was still in its infancy. We would phone up people and we would fax them finding charts. Now, you know what, I'm not sure how many people remember the fax days, but the fax days did not have the greatest image quality. And so faxing people blotchy CCD images that got even blotchier in transmission didn't actually endear us to many people that we were trying to say, please stop what you're doing on your telescope and take a spectrum of this distant blob. And in fact, it became almost a running joke in astronomy that you didn't want to be phoned up by Carl Pennypacker and his team to be convinced to observe something that would turn out to be a complete false alarm. Indeed, when we were observing with this system, many of us would draw the short straw to have to phone up a much a more senior astronomer. We were all still young and naive at that stage to convince them to spend their precious time on some of our less than convincing candidates. So as a result, during that period, we discovered no supernovae. And there it might have ended. And this is, I guess, the only place that I can really claim to have had any input to this project whatsoever, aside from doing the observing and writing the software to reduce the data. In 1990, I moved from working at the AngloAustralian Telescope to working in Cambridge for the Royal Greenwich Observatory, which was then running telescopes on the Canary island of La Palma. And one day, Carl Pennypacker phoned me up and said, look, Brian, we've kind of given up on the Anglo-Australian Telescope. The weather's not good. Our instrument isn't well suited to it. But I do have a new detector, this time a 4K detector. Is there anywhere you think of I could put it? And I said, well, actually, the Isaac Newton telescope that the Royal Greenwich Observatory was running in La Palma would be an ideal place to put it. And so we moved the project from Australia to the Canary Islands. And indeed, at the same time, we also moved the project to another telescope in Chile, the Victor Blanco 4-meter Celotololo 4-meter telescope. And so we restarted the imaging project on these telescopes where the weather was perhaps more conducive to observing. It didn't rain as much as you can see from the photos. There's nice blue sky in both those photos. Of course, we still had the problem that now, although we weren't so much sending supernovae candidates by fax and phoning people up, we now had access to much faster email. We still had the same problem, that we still had a very large amount of false positives. So again, the Pennypacker team was getting a bit of a reputation. And again, the social phenomenon is important to recognize here. Carl Pennypacker and his team had come out of Lawrence Berkeley laboratories, predominantly doing particle physics. Now, in the late 80s, particle physics was getting to a point where, unless you had mega billions, you couldn't actually participate in projects. You had to have huge teams, very expensive kit. And Carl had made the, I think, correct decision to actually focus on another area that was of interest to them, astronomy. And of course, what bigger question in astronomy was the search for the deceleration of the universe. But of course, lots of people in the astronomical community were not only skeptical of people discovering high redshift supernovae simply because it was so difficult to discover them. You had to search through hundreds of thousands of galaxies. You had to pick just when the supernova was going off. You had to follow it up. There were so many potential breaks in that chain that it was felt almost impossible. So you had a hugely skeptical, broader astronomical community that this would ever be successful. And even worse, it was being led by a team that weren't even astronomers, that had come out of particle physics. I mean, what could be more of a quixotic adventure than this? And indeed, the faculty at Lawrence Berkeley laboratories themselves were, I think, increasingly skeptical by the end of 1991 that Carl and his team could actually pull this off. Remember, I mean, it's even more so is true now, but unless you start producing results and publishing papers, particularly in professional astronomy, there is a very limited set of patience by the people that are running your university or running your institute that you should be allowed to continue. And by the end of 1991, this project now had been running for 3 years. It had produced nothing apart from a lot of grumpy senior astronomers because they had been, phoned up, faxed, or emailed in the middle of the night to stop their observing to go and observe. Nothing. It proved to be false positives. I remember going over to Berkeley in late 1991 and speaking to Carl's bosses, basically to plead for the project to be continued. I remember saying that these people are doing fundamental work. They'll put limits on the deceleration parameter of the universe. I famously said they won't win a Nobel Prize, but you'll probably get a few good publications out of it. Just shows you how perceptive I am. Anyway, everything changed. In 1992, we finally convinced somebody to take an image that was of an object that was actually a supernova. We had our first supernova confirmed using the larger William Herschel telescope, which sits next to the Isaac Newton telescope on the island of La Palma. And this object was at a redshift of 0.46. We cracked it. We'd actually shown that you could detect a supernova in a distant galaxy through imaging and through differencing images taken 3 weeks apart, and then convince somebody on a large telescope to take an image or take a spectrum of that object to measure its distance. We were off. And so we started to get a much slicker way of running the project. And at this time now, Saul Perlmutter had taken over from Carl. Carl was actually much more interested in public understanding of science and using some of these images that we were taking to work on a project called the Hands-On Universe. Still very much involved in the project, of course, but Saul, who had dedicated his career to date to the relentless pursuit of discovering these supernovae. And I give Saul huge credit when I think the rest of us on the project team kind of had almost given up. Even the project team itself had almost given up on believing that we could ever detect a distant supernova. Saul kept on going. It was him that took over the phone lines, calling everybody to follow up these objects, convince everybody that they should be using their telescopes to either detect the initial supernovae going off through imaging or to follow them up using spectroscopy. So the strategy was now clear. Every observing season, you would take a number of images of 50 to 100 fields covering 100,000 or more galaxies. You would take that just before the full moon, and then 3 weeks later, using a dark moon, you would follow it up. You would detect any supernova on the rise that had gone off, and then you would follow up with detailed spectroscopy on large telescopes, such as the Keck 10-meter telescope. And slowly we began to discover more and more supernovae. Of course, at the time, we also had competition. Although we had been the first team to start this, our success, of course, had attracted other people's interest. And another team, led by Brian Schmidt from the Australian National University, was our opposition. Now, famously, of course, there's many stories of the rivalry, sometimes friendly, sometimes perhaps not so friendly between the two teams. And you know, while things are said in the hurly-burly of the moment, no doubt, I think that both teams, I certainly know that both teams felt that in the end, it was absolutely essential we have two groups working on the program together, to some extent to keep each other's team, I'm saying honest, but certainly to keep us on our mettle and our toes, and ultimately, of course, to corroborate what turned out to be an extraordinary result. So this gives you some idea of the data that we were gaining from the telescopes. On the right, you can see the black and white images, inverted negative images of the galaxies. And again, it's not exactly the most obvious, but in the second image from the top here, you can see the supernova going off just to the bottom of the galaxy, second from the left. It then goes away again. And then on the right, on the left, you can see a spectrum taken of that distant galaxy, which measures its redshift at a redshift of 0.58. This was supernova 1994 AM. So in 1997, by this point, we had 7 supernovae, and we were very conscious, the team was very conscious that, of course, we had competition in Brian Schmidt's team, and so we published. By this time, you see also another sociological phenomenon. The team had grown from the original 6 to now over 20 people, simply because, of course, the logistics of doing what essentially turned out to be a global search over the world's telescopes for these things. Now, I've got a lot of words on the slide, but I'd like to draw your attention to 2 things. First of all, from the first 7 supernova, our determination was that the mean mass density of the universe was 0.88, with very, very large error bars, so almost 1. So essentially a very standard, very normal cosmology with matter dominant. And in fact, we also, of course, looked at the cosmological constant, if we could measure the cosmological constant. This time we expressed it as the mean energy density of the universe. So the cosmological constant was 0.06 with large error bars, but essentially we were almost ruling it out at the 95% confidence level. And this was in a paper written in 1996. So even for the first 7 supernova, we were already showing hints that that lambda, the cosmological constant, could well be 0. Now, all that changed a year later. And I'm going to show you this diagram. It's a bit busy, but I think it gives you a sense of what we discovered and the confidence with which we discovered it. On this slide is a plot of, on the y-axis, relative brightness, with faint being towards the top and bright being towards the bottom. And on the bottom axis is the scale of the universe relative to today's scale, or redshift. So you can see that all the dots on this diagram are the supernova discovered not only by the Supernova Cosmology Project, but also by the high redshift supernova search, Brian Schmidt's team. So we're putting all the data together now, although this is post facto, because we didn't put it together for the observations, for the papers, I should say. So what you can see here is, as you move along in terms of scale of the universe, you can see that the supernovas we're detecting, so We're measuring their redshifts through their spectrum, and we're measuring their relative brightness from the direct observations of the images. And you can see here that there's two lines. There's lines where you would sit if you were in a decelerating universe, whereas matter was dominant, the universe was slowing its expansion down, and we didn't see that. What we were seeing in the main, although you can make your own judgment from this signal, that most of the points lay above the line which said that the universe was empty, that there was no actual deceleration of the universe at all. In fact, because the objects, the supernova, were actually much fainter than we expected them to be, i.e. further away than we expected to be, even if the universe wasn't slowing down, that means that the universe had to be, well, what's not slowing down? It's accelerating. So the very fact that these objects were much fainter than we expected them to be, even if the universe hadn't been slowing down, was that the universe was accelerating. That there was some other thing other than matter in the universe causing the objects to be much further away than we expected. An acceleration, a cosmic repulsion of the universe. And it was this discovery that was so alarming. I mean, alarming to us as well, because only a year ago we published a paper that had said that everything was pretty much standard, that the amount of mass in the universe was roughly equal to the critical density, and lambda was quite low. And yet a year later, when we really looked at the data, we gathered more data, we discovered the inescapable fact that the universe wasn't exactly like that at all, that in fact it was accelerating. And indeed, Saul made the announcement at the Astronomical Society meeting of the American Astronomical Society meeting on the 8th of January 1988, and Science reported this is probably pretty accurate. Perlmutter presented the SC, the Supernova Cosmology Project, hard-won data, you betcha, pointing to a cosmological constant, a term introduced into the equations of general relativity by Albert Einstein, but later rejected him as a mistake. Over the course of a decade, from 1988 to 1998, using novel methods in the face of intense initial skepticism, you betcha, the project team had gathered evidence that showed, to the surprise of most scientists, including themselves, that there was something else in the universe besides mass and ordinary energy, and Einstein had not been mistaken after all. Well, I don't know whether Einstein was mistaken or not, but it was an immense surprise to us. And so we now, instead of just the mean mass density of the universe being due to matter, we have the mean energy density of the universe, including a contribution from the cosmological constant. And discussion of things like Q naught was gone away. So here's the paper from our discovery paper, led by Saul. You notice that we actually waited until we had 42 high redshift supernovae because we were kind of fans of the Hitchhiker's Guide to the Galaxy. And for many of you who also know that ancient text, that 42, of course, is the answer to the life, the universe, and everything. We thought it quite cute. But you know, in the end, we had to publish, of course, because Brian and Schmidt and the high redshift supernova team were hot on our heels. In fact, they published slightly earlier than us their discovery, but essentially it was contemporaneous. And if you read down in the text there, we found that now with much better error bars, that the mean mass density of the universe was only 28% of critical, and that the energy density of the universe, that is through lambda, was much closer to 80% of critical. And so this actually is probably the best representation of our data that we found. The blue ellipses are the, if you like, the errors on the data on the results from our data. So you can see that we essentially were able to constrain one part of the lambda matter variables. So essentially, we were saying that lambda was non-zero to a very high degree of confidence. We had discovered the acceleration of the universe. Fortunately, at that time, we also had completely independent measures, not only from Brian Schmidt's team that confirmed our results, but also from people working on the cosmic microwave background and from clusters of galaxies, all of whom doing completely different methods. The clusters of galaxies was more of a standard ruler method than a standard candle method. And the error regions for omega mater and omega lambda were all quite different as a result. And the only place that all these three results gave was in an omega mater of around about 0.25 and an omega lambda of 0.75. The universe was dominated by lambda, by dark energy. And that meant that the universe, of course, would continue to accelerate. In fact, the omega lambda term, the cosmological constant term, would increase with cosmic epoch. So that essentially, this was the only universe we had. This is the only universe we got. So we are now, through our observations of supernova, identified that the universe was accelerating, that the cause of this acceleration was this thing that we called dark energy. 72% of the stuff of the universe was dark energy. 23% of the universe, the remaining was just matter. Now, of course, of that remaining matter, we know from baryosynthesis that only 5% of that matter is in normal matter, the stuff that you and I and stars and galaxies are by and large made of, and that 23% is some form of dark matter, some supersymmetric particle perhaps that we have yet to detect. And remember also that there's another unappealing thing about this, is that that's the stuff of the universe today. As I said, in the distant future, dark energy will become more and more dominant as the universe flies apart and the density of matter gets lower and lower. And on the other token, of course, very early on in the universe, the composition of the universe, the mean density of the universe was composed very differently as well, with the preponderance being in dark matter. And again, here's another unappealing thing about this. Right now, today, in the universe, we're at a point where dark energy and dark matter are roughly the same, at least to within an order of magnitude. And many people have said, well, that's fine tuning. How could it be so close to each other today when it's orders of magnitude different in the future, and it's been orders of magnitude different in the past? Another argument against dark energy is that the standard models of dark energy would predict a cosmological constant that is 120 orders of magnitude greater than that which we observed. Now, you say, well, greater? Isn't that also a problem? Well, it's not a problem for the people who derive these things, because then they simply say, well, it must have disappeared in the past. But it's really difficult. You can make things completely disappear, but getting them to disappear to only 120 with 120 zeros after it, less than it was before, is actually quite difficult. So I'd also like to say a few words about Sol as well here. Sol, who eventually, of course, was recognized with the Nobel Prize for Physics in 2011. I have never worked with someone who was more charming or more humble or more generous. In all Sol's work, he was very careful to fully recognize all the members of not only his team, but also the competing team as well. This is a classic quote from Sol in one of the Physics Today articles that he wrote. So I've listed in full the members of the High Supernova Search Team, High Redshift Supernova Search Team, and the Supernova Cosmology Project teams, because each of these scientists should be recognized for important contributions to the discoveries described here. It's been both an honor and a pleasure to work closely with my colleagues who dedicated themselves to work for years on end, providing creativity and leadership. Well, Sol, thank you. And, it was a privilege to work with Sol as well. And if you asked anyone on the Supernova Cosmology Project team who could be more deserving of the Nobel, nobody would challenge Saul's right to be acknowledged with that role, with that award, I should say. So, as I said, here we have a picture. It's not a great picture, but it's the picture that I took from the gallery, watching the Nobel Prizes in 2011. And Saul is the person on the very left, standing up, waiting to receive his award. So Saul invited the entire Supernova Cosmology team to Stockholm for a week in December 2011, and we had an absolute blast. One of the most enjoyable weeks of my life. Sweden's a very special country that treats people who have achieved some form of academic excellence with amazing respect. I mean, we were fated like rock stars for that week. Endless parties and visits to embassies and what have you. It was just an amazing experience. And you saw us what we looked like when we started the project. Well, this is Saul and me at the one of our team dinners earlier on. We got a little bit older in the meantime, but I think just as full of life and energy as ever. So, of course, all that was a long time ago now. And I think when Saul and, of course, Brian and Adam Rees were awarded the Nobel Prize for the work that they had done, there was a degree of I don't know. The Nobel Prize acknowledged the work quite soon after the work was done. The Nobel Prize was given in 2011 for the papers that we published in 1998. So less than 13 years after we made the paper, and that's relatively quick for a Nobel Prize. In fact, even though by this time the teams had swelled to, I think, 30 or 40 people on both sides, there was remarkably few people who died before the point of being awarded, before the Nobels were given. But people felt it was almost indecent haste. And since the paper, indeed, since the Nobels, people have rightfully asked the questions. Well, are supernovae 1A really standard candles? How do you know that there isn't some cosmological evolutionary effect that's causing them to get intrinsically dimmer? So even though you think they look fainter than they should in a normal universe or a normal matter-dominated universe, so you've got to put this deceleration in. Perhaps it's some evolutionary effect. Now, people have looked at that repeatedly, and every time they look and do tests for that, it comes up with a demonstration that, as far as we're aware, they look to be fundamental standard candles. But what about the Hubble discrepancy? Even just a month or so ago, the latest paper published showed that there is still a discrepancy between the values of the Hubble constant. In a thing that sounds very similar to 30 years ago, albeit the scale is quite different, we now have two camps. That is the camp that argues for a Hubble constant of 67 kilometers per second per megaparsec. That's the camp that have studied the cosmic microwave background and using the now standard lambda, dark energy, cold dark matter concordance model, where we saw those observations come together. That is 72% dark energy, 25% dark matter, and the rest in normal matter. Or the people who directly observe it using standard candles, 74 kilometers per second per megaparsec. And indeed, there's more than just one type of standard candle now that we use to get Hubble's constant. And each one of them are turning up numbers that are higher than 67. Now, the error bars on each of those numbers are typically 1 to 2 kilometers a second. So arguably, it's a significant difference between the two versions of the Hubble constant. Now, the people who are doing standard candles saying we've done lots of different standard candles and we're getting a constant 74 kilometers per second per megaparsec. We know the CDM is right. The one unknown in all of this, of course, is the cosmological model you're using to infer the 67 kilometers per second per megaparsec. That is the lambda CDM model. So perhaps that model needs revision. So it's very similar to where we were 30 years ago. In fact, arguably, the difference in the Hubble constant is actually driving a much more critical view of our current cosmology. So, did we get it wrong? I kind of hope so. I kind of hope that there will be young people out there right now who will make a discovery like we did 30 years ago that completely challenges and upsets the orthodoxy. Whether or not you believe, not believe, but think that the lambda CDM model, a universe dominated by dark matter and dark energy, is the best explanation we've got, or it's some kind of 21st century epicycle on the universe, you must always constantly challenge what the current model is. Science only, and astronomy only moves forward by the existence of the falsifiable hypothesis. You always have to be prepared for your hypothesis to be challenged and celebrate when your hypothesis is shown to be wrong, because that's how science moves forward. I feel very lucky to have been part of this amazing journey to discover that the universe was accelerating, that we have a universe dominated by dark energy. And I will be even more elated to find out that we were only part of humanity's journey of discovering more and more about the universe. Thank you very much.
Thank you, Brian. That was a fantastic presentation. I certainly really enjoyed that one. We do have a few questions, and I'll just go through. I do have one of my own to start off with, actually. The whole story about searching for supernovae was really interesting to me. We've got a country member of the society who's an amateur who's discovered well over 100 supernovae from his farm, Stu Parker. I assume you've probably heard of him over the years, and he's given some fantastic a fantastic talk to the society in the past on that. What I was going to ask is, obviously, the search for supernovae carries on. There's survey telescopes that try and do this faster than the amateurs and the people who are doing this manually now. But what role is the search for supernovae playing now in astrophysics and in determining the cosmology?
Well, look, again, a large part of it is to refining how much of a standard candle these objects actually are. I think it's really important to continue to look at that. It's one of the areas where I feel uneasy about the body of data on which the identification of dark energy is based. So I think the more and more we know about supernovae of all kinds is really, really important, because they're it's the fundamental building block for this whole result.
Thanks for that. Okay, 3 questions. John Drummond wants to know the first supernova you discovered, the one with a redshift of 0.46. What magnitude was that?
Oh gosh, that's a really good question. It was, I'm going to say it was probably about 22nd magnitude.
Yep. Bill the president did a bit of a read off your charts, and he came back with he thought it was between 22 and 23. So that was good guess, Bill.
Yeah, that was look. My memory is. I think I didn't go into that into some detail, but I'm sure, because I'm sure your members are reading these things off. These things were phenomenally faint. They were just blips, and you can imagine sending through a finding chart, a faxed finding chart of a 22nd magnitude object to a senior professor of astrophysics and asking him to stop what he was doing or she was doing on a large telescope and observe this, what could have been anything from an error in the fax machine to, an error in our flat fielding of the data. Somebody once said in a book talking about this that the internet was being invented around these teams. And so just the business of transferring large amounts of data from the telescope back to the Lawrence Berkeley laboratory, where most of the data analysis was being done, was a huge undertaking. We used to get the old dial-up modem going every night, and it used to beep away. I used to take home, I don't know how many of your members remember the old 6250 bytes per inch tape, big reel-to-reel tapes that you used to have. I used to take rucksacks full of these things back home, and I'd only be lugging a few hundred megabytes. The thing I can put a gigabyte or 2 gigabytes in a matchbox, or put several of them in a matchbox these days. It's quite different. So the whole communications data storage revolution was happening at the same time, and to some extent that's the reason why we got more and more successful. But there was also a sociological reason we got more and more successful, and I think that was the more important one, is that people didn't believe us. Yeah. And more importantly, people didn't believe we could do it. We didn't believe we could do it.
Another question from a user called Chemistry Guy, who says, what evidence do we have that the rate of change of acceleration of the universe is a constant?
The rate of change. Well, people have, it's interesting. So this is something called I think he's referring to the equation of state of the universe. And people have suggested that you can look at the next derivative of the deceleration of the universe and see what you can, and that would tell us something about the nature of dark energy. As far as we can determine, it's not changing. So the acceleration is constant, as you might expect from a standard dark matter model. But again, watch this space.
We've got a couple of questions from Ken. First question here is, there is some evidence that the universe is not completely isotropic. If that is the case, how does that impact the analysis of the Type 1a supernova results and the dark energy conclusion?
Oh gosh, that's a good question. Yes, if the universe is well, it depends in what way it's non-isotropic. If it's non-isotropic, then it might affect things like the Hubble constant, the expansion of the universe, and it might also affect the acceleration of the universe. It depends in which way. I think if the universe is anisotropic, then almost all bets are off on what the model of the universe actually is, because we've got something really wrong with the universe. So I think if the significant anisotropy of the universe is wrong, then things like, of course, things like the flatness of the universe, the fact that everything adds up to the critical density, which is really coming largely from the cosmic microwave background observations. Again, that throws all that into doubt, because we have the theory of inflation, where the universe went through a massive inflationary period in the very early stages of the universe, which caused the universe to have large-scale isotropy and ends up with the mean mass density of the universe being equal to the critical density. Well, that's all challenged as well. So anisotropy of the universe would challenge the fundamental foundations on which this concordance model is based. So really good question. Yes, if that's the case.
Another one from Ken then. The Type 1a based analysis did not take into account local motions in our patch of the universe. Does that raise doubts about the conclusion that the expansion of the universe is in fact increasing?
Look, another good question, but no, the standard candle nature of I didn't go into details about that, but you also have to make a lot of corrections. When you make the observations, you have to make corrections for metallicity of the supernova, the metal content of supernova. You have to make corrections for the opacity of the ejecta of the supernova, and also you've got to make cosmological corrections, as you say, for local deviations from the Hubble flow. But once you get through all those, I think we can safely say that impact on the standard candle nature of the supernova is accounted for. There's other stuff that clearly it may not necessarily be accounted for. That's why I say continued observations of supernova 1a in this case are really important. And of course, it doesn't rule out the fact that things like a potential anisotropy in the universe, or the fact that the Hubble constant's not matching up between observations and inferred Hubble constant from the cosmic microwave background, all of those could potentially challenge the result. I certainly don't want to come across as someone who is defending the lambda CDM model and the acceleration of the universe. And I think there are areas in which it seriously can be challenged, as is what should happen in good science. But I think the local deviations in Hubble flow are not the way to challenge it. Anisotropy certainly is.
Okay, thanks for that. Final question, unless anybody gets one in really quickly. This one's from Bill, and he wants to know, will these projects continue using the data from the soon-to-be-commissioned Vera Rubin Observatory?
Yes, no, the whole the Supernova Cosmology Project team, even though I've not been a member of it more or less since the paper that we produced in 1998, continues to work very strongly on all aspects of the supernova cosmology and what we can derive from it.
Final comment, not a question, from Bill, which certainly I echo. Bill says, "Hi Brian, thanks for this fascinating talk on the history of the SCP. We hope to be able to invite you to visit us at Stockholm next year once the COVID-19 pandemic is hopefully over or under control." So yeah, I'd like to echo that and say thanks very much for a fantastic, really interesting talk. You would never know that you've never done a virtual presentation before. It was fantastic. I certainly really enjoyed it, and I'm sure our members did too. So thank you very much.
Well, thank you for giving me the time. It was a real pleasure, and I do hope that people learn something from listening to an old campaigner recount his war story.
All right, thanks very much, Brian.
Thank you. Bye.